Good morning, everyone. My name is Bingyang, a fourth-year PhD student from Peking University. I'm glad to share our work, FastServe, iteration-level preemptive scheduling for large language model inference. Today, large language models power many interactive AI applications, such as chatbots, coding assistants, and copilots. For example, weekly token usage on OpenRouter has increased by about 15 times in 1 year. Therefore, improving LLM inference efficiency while providing a good interactive user experience is increasingly important. The LLM inference follows an autoregressive pattern. When a request arises, the large language model serving system treats it as a job and performs inference in 2 phases. The first phase is the prefill phase. In this phase, all input tokens are processed in a single iteration, and the model prepares the internal state for generation. The second phase is the decoding phase. In this phase, the model generates 1 output token in each iteration. The generated token is then used as part of the context for the next iteration. This process continues until the model generates an end-of-sequence token or reaches the maximum output length. A key point is that the input length is known when a request arises, but the output length is unknown. This makes the total execution time of an LLM inference job difficult to predict. A key optimization in this inference process is the key value cache, or KV cache. During the prefill phase, the model computes and stores the key and value tensors for all input tokens. During the decoding phase, the model only needs to compute the key and value tensors for the newly generated token, and it can be reused in the previous tensor from the KV cache. This avoids redundant computation and is essential for efficient LLM's inference. However, KV cache also introduces a major memory challenge. As the input length and output length become longer, the KV cache grows linearly with the sequence length. For large models, the KV cache consumes a large amount of GPU memory. So KV cache is both a performance optimization and a memory bottleneck. To serve LLM inference efficiently, previous LLM serving systems often use request-level continuous batching. The system sets a maximum batch size based on latency requirement and GPU memory constraint. When the number of running requests is below this limit, new requests can be added into the batch. When requests finish, they are removed from the batch. This improves GPU utilization compared with static batching. However, once a request is scheduled, it typically runs to completion. This means the scheduler makes decisions at the request level, not at the iteration level. As a result, a long request may occupy a batch slot for a long time. Later requests, even short ones, may have to wait until earlier requests finish. This creates headline blocking. This slide shows why headline blocking is especially serious for LLM inference. In the example on the left, some requests have long outputs. If these long requests are scheduled earlier, later short requests cannot start immediately. They have to wait in the queue, even though they may only need a small amount of computation. The figure on the right shows the latency breakdown. For real workloads such as ChatGPT and Alpaca, queuing delay can dominate the end-to-end latency when the load increases. This observation is important. Optimizing only the execution time is not enough. To improve LLM inference performance, we must also reduce queuing delay. To address this problem, our key insight is simple. LLM inference naturally proceeds iteration by iteration. In the decoding phase, each iteration generates 1 output token. Therefore, after each iteration, the system has a natural opportunity to make a new scheduling decision. Therefore, we propose FastServe, an LLM serving system with iteration-level preemptive scheduling. FastServe uses this opportunity to enable preemption and the granularity of iterations. Instead of forcing a request to run to completion, FastServe can decide whether to continue running it or preempt it and schedule another request. This design helps eliminate headline blocking caused by run-to-completion processing. The system has 2 main components, a skip job and a queue scheduler for deciding which job to run, and a proactive KV cache swapping mechanism for handling memory overhead of preemption. The first challenge is that the total job execution time is unknown. If we knew the exact remaining execution time of every job, then the shortest remaining processing time, or SRPT, would be a strong scheduling policy for minimizing average latency. However, LLM inference does not give us this information. The input length is known when the request arises, but the output length is not known in advance. A request with a short input may generate a long output. and the request with a long input may generate only a short output. Both input length and output length affect the total execution time. This makes it difficult to directly apply scheduling policies such as SRPT. A natural Roman solution is multi-level feedback queue, or MLQ. MLQ is designed for settings where we do not know job execution time in advance. A new job started in the highest priority queue. If it keeps running and consuming its content, it is demoted to a lower priority queue. However, naive MLQ does not fit LLM inference well. The reason is that the prefill phase can be much longer than the later decoding iterations. As shown in the figure, the iteration time depends strongly on the input length. If the prefill time exceeds the content of the highest priority queue, the scheduler faces a dilemma. If it preempts the job in the middle of an iteration, it loses intermediate computation and must recompute. If it waits until the iteration finishes, then headline blocking can still happen. To solve this problem, FastServe proposed skip join MQ. A key insight is that LLM inference is not completely information agnostic. Although the output length is unknown, the input length is known. Since the input length can determine the prefill time, we can estimate the first iteration time using lightweight profiling. Instead of always placing a new request into the highest priority queue, FastServe places it into the highest priority queue whose content is large enough for its first iteration. This is why we call it skip join. The request skips the queues that are too small for its prefill time. After that, FastServe demotes jobs based on their current priority and next iteration time. It also periodically promotes low priority jobs to prevent starvation. In this way, FastServe reduces unnecessary demotion while still adapting to unknown output lengths. This slide illustrates an example that compares 4 scheduling algorithms: FCFS, naive MQ, skip join MQ, and SRPT. SRPT is Oracle policy because it knows the full job size in advance. Its average latency is 3 in this example. Skip join MQ achieves an average latency of 3.3, which is very close to SRPT. In contrast, FCF has an average latency of 4.2, and naive MQ has an average latency of 5. Both suffer from headline blocking in different ways. The key difference is that skip join MQ recognizes that the first job has a long prefill time and places it into a lower priority queue directly. This allows shorter jobs to run earlier, so skip join MQ approximates SRPT without knowing the output length in advance. The second challenge is GPU memory overhead. With FCFS scheduling, LLM inference serving system only needs to keep KV cache for currently running requests, but with preemptive scheduling, LLM inference serving system also need to preserve KV cache for preemptive requests. Otherwise, when a preemptive request resumes, the system will need to recompute its previous state. The figure shows that MQ can consume much more KV cache memory than FCS. This is because more jobs are kept in the system at the same time. So this overhead is significant for large models. The KV cache of a single request can already be very large, and GPU memory is limited. Therefore, preemption improves scheduling flexibility, but it also creates a serious memory management problem. There are 2 simple strawman solutions, but both have problems. The first solution is to defer newly arrived jobs when GPU memory is full. The system waits until current jobs finish and release memory, but this brings us back to the FCS behavior and reintroduce headline blocking. The second solution is to kill some low priority jobs and release their KV cache. This gives memory to new high priority jobs, but it wastes expensive GPU computation because the kill job must rebuild their KV cache later. Even worse, this can lead to a live log-like situation. A kill job may be promoted to avoid starvation. Then it may preempt another job, and the system can repeatedly kill and recompute jobs. So we need a better memory management problem. To address this problem, FastServe uses priority KV cache swapping. The key observation is that a job KV cache only needs to be in GPU memory when the job is going to execute soon. Otherwise, the cache can be stored in host memory. FastServe therefore extends the KV cache storage from GPU memory to host memory. It proactively offloads inactive KV cache to CPU memory, keeps some idle GPU cache source for newly arrived jobs, and proactively uploads KV cache that are likely to be used in the near future. The important part is that this is proactive, not reactive. By leveraging scheduling knowledge, FastServe overlaps KV cache transmission with GPU computation. As a result, PCIe transfer overhead is mostly hidden and does not stay on the critical path of inference. Please refer to our paper for more details. Now I will present the evaluation. The paper includes a broad set of experiments. In this talk, I will focus on the first three results. This slide shows the end-to-end performance on real workloads. We evaluate FastServe and state-of-the-art systems like vLLM using different sizes of models on the represented workloads such as ChatGPT and Alpaca. As shown in the figure, FastServe consistently supports a much higher arrival rate under the same latency SLO. Compared with Fast Transformer, FastServe improves throughput by 31 to 74 times. Compared with vLLM, FastServe improves throughput by 2 to 6 times. The FastServe FCS baseline uses the same execution engine, but keeps FCS scheduling. FastServe still outperforms it, showing that the scheduling design is a major source of improvement. We also evaluate the effectiveness of each component separately. First, we evaluate the effectiveness of skip-join MQ. We compare skip-join MQ with the FCS fixed priority scheduling and naive MQ. We vary the ratio between input length and output length to represent different workloads. FCS consistently suffer from headlight blocking. Naive MQ works better when prefill and decoding times are similar, but it performs poorly when prefill time becomes longer. Fixed priority works better when the input length dominates, but it ignores the uncertainty of output length. Skip-join MQ combines the advantage of these approaches. It uses non-input length information for the prefill time, while still adapting to unknown output length through MQ demotion. As a result, it improves performance by up to 8.9 times over FCS, 1.8 times over naive MQ, and 13.9 times over fixed priority. We also evaluate the effectiveness of proactive KV cache swapping. We compare three memory management policies: recompute, reactive swapping, and proactive swapping. At low request arrival rates, GPU memory is sufficient, so the three methods perform similarly. At higher arrival rates, GPU memory becomes the bottleneck. The recompute policy discards KV cache and rebuilds them later, which wastes GPU computation. Reactive swapping moves KV cache only when memory is needed, so the transfer cost is on the critical path. Proactive swapping performs better because it anticipates future scheduling decisions. It offloads and uploads KV cache in advance and overlaps data transfer with computation. This gives 2.7 times throughput improvement over recompute and 1.7 times over reactive swapping. The latency breakdowns also shows that the visible swapping time is small because most of the transfer overhead is hidden by overlap. To conclude, FastServe is a fast LLM serving system that enables iteration-level preemptive scheduling. The main problem we address is headlight blocking in existing run-to-completion LLM serving system. FastServe solves this by exploiting the autoregressive generation pattern of LLM inference. There are two key techniques. First, skip-join MQ uses input length information to place new jobs into appropriate priority queues and reduces unnecessary demotion. Second, proactive KV cache swapping uses host memory while hiding most swapping overhead through overlap. Our evaluation shows that FastServe improves throughput by up to 6.1 times compared with vLLM and achieves much larger improvement over Fast Transformer. Thank you for your listening. I'm happy to take questions.